Hey everyone, this is Whit from Brainstem Tutoring, and today I wanted to talk about a question like this. I would call this a burst of photons problem. It's super typical on the Clemson Chemistry 1 exam. Let's read it together. It says, an orange laser pointer with a wavelength of 590 nanometers emits 2.60 moles of photons. How much energy is in this burst of photons in kilojoules? I literally said the word burst of photons, but it doesn't have to literally say it. It can be collection of photons, group of photons, any sort of synonym like that. Now, the first thing we're going to do is focus in on the wavelength of a single photon. Go back and watch the other video on how I break this down, but first we want to convert that to the energy of a single photon. So, to do that, C is equal to lambda V. So therefore, 3 times 10 to the 8th is equal to 5.9 times 10 to the negative 7th meters times V. Solve for V, or that's frequency. And I have this in my calculator. Let's see. I believe that is 5.08 times 10 to the 14th seconds negative 1, also called hertz. Now you take that, and the energy of this orange photon should be Planck's constant times the frequency. So the energy of this single photon should be 6.626 times 10 to the negative 34th joules times seconds. That value would be given to you, times the answer we just got, which is 5.08 times 10 to the 14th power, 1 over seconds, seconds to negative 1, same thing. And we get that the energy of a single orange photon would be 3.37 times 10 to the negative 19th joules. Try your best to not round throughout the problem. I know I wrote rounded answers, but I have them all in my calculator. Okay. Here's the new idea. This equation won't be given to you because it's sort of logic. The best analogy we can use for energy is money. Let's say I had a bagel, and a bagel cost $2. If I wanted to buy 10 bagels, think about it for 2 seconds. And how much money would that cost total? That's supposed to be a dollar sign, my bad. You probably said, oh, if each bagel is $2 and I have 10 of them, you multiply to get the total amount of dollars. If you thought $20, that's exactly right. That's logic. That's math too, but that logic is going to be super duper helpful. What if we could calculate the energy of a single photon? Hint, hint, we just did that. And you could multiply it by the number of photons. Well, through that same logic, it would give you the energy total of a group of photons. And that is exactly what the question's asking for. So, we already know the energy of a single orange photon, but let's first work on the number of photons. In the original problem, it told us, hey, we have 2.6 moles of photons. Here's where people get led astray. That does not mean, it's not the same as saying 2.6 photons. Moles is a very, very specific number. It's a group. It means I have 2.6 Avogadro's numbers of photons. So, a little bit of algebra real quick. That means I have 2.60 times, I guess I don't need parentheses, times Avogadro's number. So the number of photons should be 1.57 times 10 to the 24th photons. Wonderful. Now that we know how many photons there are, and if I copy and paste, we know how much energy is in a single photon, and multiply the two together, that will give me my energy total. But be extra careful about units. They're there to trick you, it feels like, on this problem. When you multiply those two things together, we should get that the energy total is equal to 527,500 joules. Sort of rounded 4 sig figs. Now, I've obviously written what unit we're talking about or what my answer is in, but go back to the original problem. That is not what they want. So don't forget, for every 1,000 joules, you have 1 kilojoule. Essentially, we're dividing by 1,000. And our energy total would be 527.5 kilojoules. Be careful about units. Be careful about this logic. They won't give that to you. Don't forget that they could also rearrange it. Let's say they gave you the energy total and wavelength to figure out energy of a photon. They might ask you, hey, how many moles of photons are in this burst? Or they could give you the energy total and number of photons and say, how much energy must have been in that singular photon? In order to do well on a chemistry exam, you need to be prepared for those other cases. I always say to students, if you go from A to B, A to B, A to B, and practice it 100 times, and never practice going from B to A, going backwards through a problem, you're susceptible to not doing well in the exam. So try to think about how you would have gone through this problem if I gave you different information. Be careful about units. Take your time. Don't screw up plugging things into your calculator. And good luck with problems like these. And if you have any questions, please reach out. Thank you.